Previously in the DOS journey, scheduling is the process that determines the start time of each operation in hardware. The classic approach to scheduling is static, which maps each operation into a clock cycle at compile time. It can generate area-efficient hardware, but the schedule is very inflexible and could be very slow for some applications. Recent years have seen the emergence of dynamic scheduling that determines an operation's clock cycle at runtime. It has a flexible runtime schedule, potentially achieving a better performance. But the area is quite expensive. Thus, it is proposed to combine the best of two worlds. It has the mechanism of dynamic scheduling, also the area efficiency of static scheduling. However, a problem still exists in using DOS. We still need an expert to decide which scheduling methods should be used for each part of the code. And today, we present an automated solution to get rid of this pain in the DOS. Hi everyone, my name is Jianyi Chen, and I am a PhD student at Imperial College London. This work is built on the existing open-source HOS tool named DOS. It allows statically scheduled components integrated into a dynamically scheduled circuit to get a more efficient hardware design. These statically scheduled components are called static islands. So today, let me walk through a few examples to show what the problem is and how we solved it. Let's get started. Say I have this piece of code in my hand, and I want to get an efficient accelerator from DOS. But I don't know anything about hardware. Hi Homer, can you help with this? Well, we all know that Homer is not that intelligent. He probably will ask Marge for help. Marge happens to be an expert of DOS. She points out that there is a loop carry dependence in the first loop. However, the if condition in the first loop makes the self-update of weight input dependent. And this is more suitable for dynamic scheduling. But the self-update statement is a simple polynomial expression. We could statically schedule the self-update statement as a static island. The second loop has a memory dependence in an array R. However, the dependence distance is always 4, which means that we can statically schedule the loop pretty well. So the whole second loop can be a static island. Here's the data flow graph of the function being dynamically scheduled. Based on the hints by Marge, DOS can statically schedule the polynomial expression and the second loop to get a good hardware design. Well, this is quite complicated and needs some expertise in hardware scheduling. And unfortunately, Marge cannot always be around. What should Homer do? If we try exhaustive search, there is a huge search space for such a small piece of code. We may even get a large and slow design if we select inappropriate constraints. People like Homer are suffering from selecting these static islands and cannot really benefit from today's DOS. We propose an automated tool to avoid such pain in manually finding static islands. Our contribution includes a technique that automatically finds an efficient set of static islands from arbitrary program. Once they are found, we use an automated path that efficiently synthesizes them for high performance. The original tool flow of DOS is shown here. It takes a C program and lowers it to LVMIR. Then the LVMIR is translated to a dot graph and later translated to an RTO design. Our tool is integrated as a plugin to DAS. It analyzes the program in LVMIR and performs hardware transformation in the dot graph. Now, let me demonstrate how to find good static islands. First, loop pipelining has been well studied in the HOS community. So let's first search for static islands in loops. Before that, let me introduce a few terms. First, the initiation interval is the number of clock cycles between the start times of the same operation in two consecutive loop iterations. I is normally used to evaluate the performance of a pipeline loop. Static loops support a constant II, and dynamic loops can have variable IIs. The II depends on two constraints. The iteration latency is the number of clock cycles between the two start times of an operation and its dependence. The dependence distance is the number of the iterations that separate an operation from its dependence. Based on these constraints, we categorize loops into a reference table. First, any loop that has a constant iteration latency and a constant dependence distance can be a good static island. For example, the latency of the loop body of the second loop does not change and has a constant dependence distance of 4. This means that the second loop can be statically scheduled without any performance loss. Okay, but how about this case? What if the iteration latency is a variable? Now, if we look at the first loop, the if condition makes the latency of the loop body depending on the array element AI. Statically scheduling the whole loop may cause worse throughput. Should I take the whole loop as a static island? If I do this, how much throughput I will lose? We build a performance model for making this decision. Let's look back to the data flow graph. Here, we only need to look at the first loop. The if condition decides which data paths are executed for the variables wait and d. The wait has 2 cycles. When the condition is false, it is directly forwarded to the next iteration. When the condition is true, it goes through the adder and updates its value. The loop iterator is independent from the if statement, so it only has a single cycle. Now assume the probability of the if condition being true is half. Our analyzer automatically extracts the throughput of each cycle and its probability. It then works out an overall throughput when dynamically scheduling the loop, and the throughput loss when statically scheduling the loop. This is a graph of the throughput loss factor over different probabilities. The more likely the if conditions are true, the less we lose in throughput from static scheduling. The probability of if condition is already obtained by profiling in a DAS tool. User can specify an affordable threshold that allows small throughput loss. For instance, any probability above the threshold indicates that the loop should be statically scheduled. By tuning the threshold, user can choose their own preference on performance and area. So the loop may be scheduled by one of the 3 approaches. It may be purely statically scheduled, or purely dynamically scheduled, or it is dynamically scheduled but its loop body can be partially statically scheduled. For this example, we statically schedule the self-update statement. We will later introduce how we find it. Okay, now we have a performance model, and we can make a proper decision on how to schedule these loops. There are more complicated cases where the dependence distance can be variable. These loops are known amenable for dynamic scheduling, which can achieve high performance by runtime memory scheduling. In summary, we specify a set of rules in finding static islands in loops. We require a static loop must have a constant dependence distance, and it either has a constant iteration latency or its throughput loss from static scheduling is affordable. We then can find a set of static loops. However, there are also restrictions by the tool that we use. Particularly in this prototype, we have Vitis address inside DAS and DAS itself. So we required the static loops must be Vitis address friendly to get efficiently statically scheduled. We also require the loops to be DAS friendly, so it has no problem interfacing with its dynamically scheduled surroundings. Finally, the rest of the loops are good static islands. If a loop cannot be statically scheduled, we then search for static islands at the instruction level. Dynamically uses a set of predefined components to form hardware netlist for arbitrary programs. We analyze each of these components and identify those that could change the throughput of the circuits. Also, our tool does not touch memory operations. These components cannot be statically scheduled, and the rest of the components can be merged into static islands. And then we can construct a set of static islands from the original data flow graph. Each island can be statically scheduled. In the data flow graph, we can see that there are some islands that contain a single component, which is the same as dynamic scheduling and can be ignored. We can also ignore those small islands as they have no space for resource sharing. We then end up with the self-updating statement as a static island. Okay, now we have the tool to automatically pick the static islands for Homer, which is great. Does it have good performance? Well, Homer tried it and told me that it is extremely slow. This is very strange. Let's have a look. DAS use a wrapper for each static island to interface with the dynamically scheduled surroundings. The wrapper synchronizes all the inputs and then starts execution. Let me quickly go through the execution. First, 2 tokens enter the loop to start. On the right, the loop iterator is forked to iterate and loads the data from memory. It then checks the if condition and loop exit condition to determine which paths this token should take. The loop iterator then goes back to the top to execute the next iteration early. Meanwhile, assuming condition is true, the branches forward weight and D to the static island. Because we have both inputs ready, we can start the execution of this static island. The execution is in parallel with outside circuit, where the loop iterator is still iterating in the graph. In the static island, the weight token arrives at the adder at the bottom. waiting for the computation of D to finish. Meanwhile, the loop iterator iterates and produces another D for the second iteration, which arrives at the input of the static island. However, the second input is blocked by the join, waiting for the second wait, even though we don't need to wait at the beginning of the execution. So we have to wait until the first D has gone through all the operations and then computed with S. The output S then loops back and arrives at the input of the static island as the input in the second iteration. This computation repeats for every iteration. Okay. So the static island is now sequential, even when the component is pipelined. That is why this is so slow. The wrapper is not aware of the fact that not all the inputs are needed to start the execution. We propose a new wrapper design, taking these time offsets of inputs in consideration. We use a shift register to count the number of cycles between the start of execution and the use of an input. This lifts the restriction introduced by the join component. Now let's try again with our new wrapper. The first iteration is quite similar, where both values simultaneously reach the static island. When the static island starts to execute, D is immediately used. The wait is not used until the last adder starts, so it is blocked at the input. But a control token enters the shift register and starts counting the stage of D. Meanwhile, the dynamically scheduled circuit continuously feeding D into the static island. This wrapper does not store the following Ds, but accepts them in the pipeline. Each D is tagged with a control token to counting the stages for itself. When the control token reaches the end of the shift register, it means that the adder at the bottom starts to execute in the next clock cycle. The first wait then enters the island and starts execution. Our new wrapper enables pipelining of the static island and can achieve better throughput. This looks good, but how good is it? Here we use the same benchmarks from the original DAS paper. We compare the designs from our tool and the manually optimized designs by experts. The x-axis is the latency in walk log time. The y-axis is the area in LUTs. So left means faster and bottom means smaller. We place the manually optimized design at 1, 1 and plot our designs using relative area and performance. We have 6 benchmarks that have the same designs as manually optimized one and 4 better ones. On average, comparing to dynamic scheduling, our approach saved 73% of the area and achieves 13% speedup. In conclusion, we solved 2 problems when using DAS: how to automatically choose good static islands and how to optimize the static islands for high performance. With our tool, the user no longer needs to suffer from such pain in the DAS. Thank you.